Okay, so good evening. I'm Calvin Joseph, and today I'm going to conduct the week 6 problem solving and doubt clearing session for this course State Space Approach to Control System Analysis and Design, which was taught by Professor A.P. Tiwari. So, the week 6 is mainly related to the concept of pole placement, and we will be looking into it. Okay, so today, what Sir has taught in this week was what is output feedback versus state feedback. And then he has taught how do we do state feedback based design, and then how companion form representation of a state space system makes it easier when we are doing state feedback based pole placement design. And then also there is the concept of pole placement and where do we place the poles. All right, so let us begin. So today is time is week 6, and we'll start with the first question. Okay, so this is the question that you consider an LTI system, and now we have to find what is the state feedback gain to stabilize the system. Okay, so let us write it. So x dot is equal to ax plus bu. So in this case, we have limited our analysis to linear time invariant systems, right? So what is my a over here? A is minus 30, sorry, minus 3003, and b is 30. Okay. So can you tell me, is this system stable or unstable? It is unstable. Why?
The eigenvalues are -3 and 3.
Okay.
One is positive.
Okay. So there is a positive eigenvalue. So eigenvalues are minus 3, comma 3. So why is this looking like this? Okay. Minus 3, comma 3. So there is a positive eigenvalue, right? So it is unstable. Now, if there's such a system, what do? We say that we cannot control the system, or we give up hope on the system? Like, what should we do in that case?
In this case, we design a controller such that the eigenvalues are on the left side.
Okay.
We get all the eigenvalues.
Okay, so we have to design a controller which will be able to, like force the system eigenvalues to be in the left side of the S plane, so we can say that the system is stable. Okay, we'll assume that. So should I directly proceed with the design, or should I check something?
We should check the observability.
Observability. How do I check observability?
We have to find the Q matrix.
Yeah, you're correct. The Q matrix, actually it is controllability, not observability. Okay. So that was B and AB. Okay. So we'll find AB, right? So this is the minus 3003. B is 30, right? So this comes out to be minus 9, and this comes out to be 0. Okay. So the Q matrix will then be B and AB. So that is 30 minus 9, 0. Okay. So is this system controllable? Hmm. Brenda? Oh, Brenda? So is it
No, the determinant is 0.
okay? Yeah, so the determinant is 0, so it is uncontrollable, right? So we cannot control the system. So that means we cannot use any state feedback gain to control the system, right? Okay. So this is just the thing. So always before you start, and what I mean to say is you have to check for the controllability everything when you're doing design. And mm, now in your exam or in your assignment and everything, they will say you must design state feedback for this system. So you may start, you will do A minus B, K, everything, and then you may not be able to design a controller or something, right? But every time you cannot find the controllability matrix and all, it can be confusing. So what I'll suggest is, since to my knowledge, like in the assignments, it's all multiple choice question, right? And I think in the exam also it will be multiple choice question only. So what you could do in that case is you can check the options. If in the options it is there, if there's an option saying that the system is uncontrollable, then you have to check. If in all the options there is no option saying that the system is uncontrollable or something, then you don't need to check because you have to assume that the system has been controllable and so there are some given gain vectors which are there. Okay, so that's the way you can save your time, right? Yeah, and the assignments are very time consuming, so saving time is very important. Okay, this is one thing. So this is the first question. Let's go to the next question is consider the LTI system. Okay, we are still considering only linear time invariant systems. The assignments also, so let's only consider linear time invariant systems. Okay, what is the state feedback gains to make the closed loop settling time of 4 seconds and the damping to be 0.5? Okay, so we go question 2 x dot is equal to what is a minus 1053 minus 1053x plus b is 3 to u 3 to u. Okay, so we can check for controllability again, and again you'll have to do the multiplication everything. So there's a simple MATLAB command. Like if you're not in the exam solving assignments, MATLAB can be really very helpful. So let me say, oh, here, controllability. I want to just check, right? I'll put the A matrix, which is minus 1, 0, minus 1, 0, 5, and 3. This is the A matrix, and this is the B matrix. 3, 2, 3, 2. So we run this section. Okay. Run this section. So this is the A matrix, this is the B matrix, and there's a simple command to find the controllability matrix, that is CTRB. You have to just feed A and B, and it will compute and give me what is the controllability matrix. And then I can use this command rank of this controllability matrix. So it will automatically, it tells me that the rank is 2. So that means my system is controllable. Okay. This is a fast, easy way to check, right? This will not be there in the exam, but I'm just floating that option to you. This might be useful when you're doing your projects and other stuff. Okay, so we have proved that this system is controllable. That means now I can design a controller. Okay, I can design state feedback gains I can use, right? So that means, what's my question? Saying that I want settling time of 4 seconds and damping to be 0.5. Okay, settling time should be 4 seconds and damping will be 0.5. So damping 0.5 usually means the damping constant 0.5. Okay, and what is the formula for settling time? For a second order system, what is the formula for settling time? Okay, so the formula for settling time actually is 4 upon zeta omega n. Okay, so what do we get our omega n to be? So zeta omega n is 4 upon settling time. So that is 4 upon 4. That means zeta omega n is 1, right? Now zeta is 0.5 into omega n is 1. So omega n will be equal to 2. Any doubts in this?
No, sir.
Okay, so this actually will be 2 radians per second. Okay, so this is like basic control system design. Like they give you what are known as your specifications. So these are your specifications. Okay, and these are actually your transient specifications because they are related to the transient response, right? They're not told that they want the steady state error to be 0 for a step input, ramp input. They have not put that. They have told these are the transient specifications that it should meet them. Okay. From that, we found out what should be our damping, what should be the natural frequency of our closed loop system. Right. From that, we can find out uh, what should be the characteristic polynomial of our closed loop system. So that our characteristic polynomial should be equal to s square plus 2 zeta omega ns plus omega n square. Okay. So that should be s square plus 2 into 0.5 into omega n is 2 s plus 2 square. Right. So that comes out to be s square plus 2s plus 4. Okay, so what will be the roots of this? Like where are the poles of this system? Okay, the poles actually are not required. The poles are not required because we just want a characteristic polynomial. Okay, so now this is our desired characteristic polynomial. So this is our desired characteristic polynomial, right? So now let us do our state feedback. Okay, so what we will do is state feedback means my input u is actually a function of the states. Okay, u, let us assume it is minus kx, right? I have assumed u to be minus kx. So my equation is what? X dot is equal to ax plus bu. Okay, let me assume p plus kx for convenience. Sorry. So it is ax plus bu. So I'll put u equal to plus kx. So I'll get x dot is equal to a plus b ax plus b k into x. So x dot is equal to a plus b k into x, right? So now I have to first find b k, right? So let me go to the next slide. What is my b? B is actually 3, 2. And what is k? K are some gains, k1, k2, right? So I will have to multiply b into k. So that is 3, 2 into k1 into k2, right? So this will come out to be 3k1 3k2, 2k1, 2k2. So this is my bk equation, right? Now my x dot has been converted to a plus bk into x. So this we can write it as x dot is equal to a closed loop into x. So my a closed loop actually is a plus bk. So what is my a? A is actually minus 1053. So it is minus 1053 plus bk. It is 3k1, 3k2, 2k1, 2k2. Okay. So that becomes equal to minus 1 plus 3k1, 3k2, 5 plus 2k1, 3 plus 2k2. So this is my a closed loop thing. So now I have to find the characteristic polynomial, right? So characteristic polynomial is given by what? Si minus a closed loop, the determinant equated to 0. So how do I find that? So Si minus a closed loop will be equal to S into 1001 minus this a closed loop. This is minus 1 plus 3k1, 3k2, 5 plus 2k1, 3 plus 2k2. Okay. So that actually is S plus 1 minus 3k1 minus 3k2 minus 5 minus 2k1 and S minus 3 minus 2k2. Okay, this is my polynomial. So now I have to find the determinant. Si minus a closed loop equal to 0. That is actually equal to S plus 1 minus 3k1 into S minus 3 minus 2k2 minus of minus 3k2 into minus 5 minus 2k1. Okay. So what does that become? So till here, are there any queries, any doubts?
No, sir.
Okay. So let me write it as, so this becomes s square minus 3s minus 2k2s. Okay. Then plus s minus 3 minus 2k2 minus 3k1s minus 9k1 plus 6k1k2. Then plus 3k2 into minus 5 minus 2k1. Okay, so that is equal to s squared plus s. I take all the terms of s, that is minus 3 minus 2k2 plus 1 minus 3k1. And the remaining terms are the constant terms, so that is plus minus 3 minus 2k2 minus 9k1 plus 6k1 into k2 plus 3k2 into minus 5, that is minus 15k2 plus 3k2 minus 2k1 is minus 6k1 k2. Okay, so that becomes equal to s square plus s to minus 2 minus 3k1 minus 2k2 plus, so here only minus 3 minus 2k2 minus 15k2. So that is, okay, so minus 9k1 minus 2k2 minus 15k2 is minus 17k2. And you must notice this 6k1, k2 and this gets cancelled. Okay. So this is our final equation. So it is very complicated maths, I admit. So we have one equation. This is our equation which we found. And what was our desired equation? Is this s square plus 2s plus 4. So we wanted our equation to be of the form s square plus 2s plus 4. Okay, so when we equate both the sides, what do we get? We get minus 2 minus 3k1 minus 2k2 is equal to plus 2, and minus 3 minus 9k1 minus 17k2 is equal to 4. Okay, so we can write it further as 3k1 plus 2k2 plus 2 is equal to minus 2, or 3k1 plus 2k2 is equal to minus 4. And this we can write it as 9k1 plus 17k2 plus 3 is equal to minus 4, or 9k1 plus 17k2 is equal to minus 7. Okay, so now what is a simple way is, uh, I write 3k1 is actually minus 4 minus 2k2. Okay, I have, see, you can use your calculator and you can solve this. Uh, but I don't think you can solve simultaneous equations using the gate calculator, which is there in the NPTEL exam. So in that case, you have to do what is known as substitution. That is, you have variable 3k1, you express in terms of k2 and the value, and then you substitute 3k1. So this can be written as what? 3 into 3k1 plus 17k2 is equal to minus 7. So that is 3 into minus 4 minus 2k2 plus 17k2 is equal to minus 7. Okay, so that becomes equal to minus 12 minus 6k2 plus 17k2 is equal to minus 7. So you get it to be 11k2 is equal to 12 minus 7. So 11k2 is equal to 5. So k2 is equal to 5 by 11. Okay, and then we substitute this over here. So we get 3k1 is equal to minus 4 minus 2k2. So it is minus 4 minus 10 upon 11. So it is minus 44 minus 10 upon 11. So it is equal to minus 54 upon 11. This means 3k1 is equal to minus 54 upon 11. So this implies k1 is equal to minus 1, uh, 8, minus 18 by 11. Okay, so the gain vector, which is k1, k2, is found out to be minus 18 upon 11, comma 5 upon 11. Okay. Hmm. So any doubts in this?
No, sir.
Okay. Yeah, so it is very mathematically intensive. It takes a lot of time. So you have to find out this equation, find out these parameters, get the characteristic polynomial, the desired characteristic polynomial, and then you have to do all this. These manipulations you have to do. Okay. So do you think there's an easier method to do this?
No, when we
Hmm?
have to do calculations manually, this is the only method I use.
Okay. There was this.
We have been used to using calculators or use
What?
MATLAB to solve. We have been used to using calculators for solving the equation.
Yeah, that's the thing. But you'll be giving the exam, right? Or no?
No, no, only the online calculators are available. It's given there.
Only?
We have to use the online calculator only, right?
Okay, okay,
Which is
okay.
given.
Uh, yeah, that's the big, very big challenge. So I don't know like how you'll be able to solve the third order matrix, its inverse, and then do subtraction. If you make any mistake, you're gone. So it's like very complicated. Should be a way. Hmm. What we could do instead, we could also try the Ackermann formula. No? Just check the Ackermann formula, whether that becomes easier. Is Ackermann. Oh, Ackermann formula is given by K is 0, 0, 0, 1 Q inverse D of A. Coefficients of the desired characteristic polynomial. Okay. Let us just check using that method. So K is 0, 1 in this case because it is second order only. Q inverse into D of A. Okay. So what is our desired characteristic polynomial? Okay, our D of A is what? If you remember, it is S square plus 2S plus 4. So it will be A square plus 2A plus 4. I think A square can be calculated easily. So what is A? A is minus 1053. So it is minus 1053. Okay, this will be 2A plus 4I. Okay, into minus 053 plus 2 into minus 1053 plus 4 into I. So this will be minus 1 into minus 1, 1 plus 0 into 5. So it is actually 1. Minus 1 into 0 is 0. 0 into 3 0. So it is 0. 5 into minus 1 is minus 5 plus 3 into 5 is 15. So minus 5 plus 15 is 10. 5 into 0 0. 3 into 3 is 9. So this is this. This is minus 2 0 10 6 plus 4 0 0 4 because the identity matrix. We add it, we get it to be 1 minus 2 plus 4 is 5. 0 plus 0 plus 0, this is 0. 10 plus 10, 20. Okay, so this is 20. 9 plus 6 is 15 plus 4, so it is 19. So this is the D of A. What is Q? Q is B comma AB. So the shortcut which I used of using MATLAB to directly find is we actually have to find the Q matrix. So what is A into B? A is minus 1, 0, 5, 3. And what is B? B actually is 3, 2. So it is 3, 2. So this is actually equal to minus 1 into 3 is minus 3 plus 0. So this is minus 3. 5 into 3 is 15 plus 3 into 2 is 6. So it is 21. So Q actually is B comma AB. So it is 3, 2 minus 3, 21. So we have to find the Q inverse. So when you find the Q inverse of a second order system, is easy. So you just interchange it. So this becomes 21, 3. And you just interchange the signs. So this will become 3 minus 2. And you find the determinant. So that is 21 into 3 minus of minus 3 into 2. Right? So Q inverse will be equal to 21, 3 minus 2, 3 upon. So 21 into 3 is 63. 63 plus 6. So it is 21, 3 minus 2, 3 upon 69. Okay, so this comes out to be Q inverse. Okay. So what's the formula? K is 0, 1 Q inverse of dA. So Q inverse into D of A. So there is 1 upon 69. Q inverse is 21, 3 minus 2, 3. D of A is 5, 0, 20, 19. So 5, 0, 20, and 19. So when we multiply, it comes out to be what? 21 into 5 is 110, no, 105 plus 3 into 20, 60. So 165. 21 into 0 is 0 plus 3 into 19 is how much? It is 57. Minus 2 into 5 is minus 10 plus 3 into 20 60, so it is 50. Minus 2 into 0 plus 3 into 19 again is 57. So this is how Q inverse D of A. So, and this is given by 0, 1, Q inverse of D of A. 1 upon 69, let it take common. So it is 0, 1, 165, 50, 57, 57. So it comes out with 1 row, 2 column, 2 row, 2 column, 0 into 1, 0, 165 and 50. It comes out to 50 here. Here it comes out to 57. 1 upon 69. So these are the values we get. Okay. So that is we are getting it as a 50 upon 69 and 57 upon 69. These are not matching with what we were supposed to get. Okay, we got was minus 18 upon 11, 5 upon 11. I think I'll have to recheck the calculations. So I'll recheck it and then I will add it. Because I think both methods are giving a different value. And now this is not a MCQ where I can check which is the correct answer or not. So this I will check. I'll have to check this. Yeah. So any doubts in this, or like were you able to, did you see any mistake I was making?
Sir, actually, I couldn't complete the calculations along with you, so I couldn't check.
You couldn't see what?
I couldn't complete the calculations by myself.
Okay. Yeah. Actually, it would be better if you also could do simultaneously. Because then some mistake would have been found probably. Anyway, I'll have to check this later, which you can proceed to the next question. So at least the steps, the flow you have got to know.
Yeah,
But I
yes,
think,
the steps I got.
but I think it is both ways are complicated. Both ways you have to take a
The
lot of.
first method, we have to solve some equations. Here, it is full matrix operations.
Yeah, matrix operations also these are quite challenging. And the problem with this is there are many places where you can make a mistake. Many places. A mistake can be very costly. Yeah. Okay. We'll see. Like we'll have to find out an easier way to verify. Verify like you can verify in MATLAB also, but then in the exam time, how to verify? Like I'll have to think what is a better way. Mhm. So we'll start with the next question. So this was the question. We'll go to this question. Okay. So here we have given an LTI system. A and B matrices are given. We have to find the necessary state feedback gains to set the poles at -1, -3, and -5. Okay. So let us start. We'll go. So this is question 3. It is related to pole placement. Here we have A, which is given by 1, 3, 4, 1, 3, 4, 2, 2, 1, 0, 2, 1, 0, 3, 1, 2. This is A. And what is B? B is 1, 0, 0. Okay. So now we have to find the pole placement. So what we do is we have to assume a gain vector K that is given by K1, K2, K3. Right? And we'll assume that our control law is U equal to minus Kx. So my x dot will be equal to A x plus U plus BU. It becomes transforms to AX plus b into minus k into x. So it is a minus bk into x. Okay, so how do we solve this? So we have to find bk. So b into k is what? 1, 0, 0, k1, k2, k3. So that is equal to k1, k2, k3, 0, 0, 0, 0, 0, 0. Okay. What is our, so a minus bk will be equal to, what is a? 1, 3, 4, 2, 1, 0, 3, 1, 2, 3, 1, 2 minus of k1, k2, k3, 0, 0, 0, 0, 0, 0. Okay, so a minus bk will be equal to 1 minus k1, 3 minus k2, 4 minus k3, 2, 1, 0, 3, 1, 2. Now to find the closed loop poles, what I have to do? I have to do Si minus A closed loop. So this is my A closed loop. So it is what? S minus 1 plus K1. So this is K2 minus 3, K3 minus 4. This will be minus 2, S minus 1, 0, minus 3, minus 1, S minus 2. Okay, so what is Si minus A closed loop? The determinant will be equal to S minus 1 plus K1 into S minus 1 into S minus 2. So this is one determinant. Minus of K2 minus 3 into minus 2 into S of minus 2 into minus 2 into S of minus 2 plus K3 minus 4 into minus 2 into minus 1. So it is 2. Minus 3 into minus 1 into S minus 1. So plus 3 into S minus 1. So, okay, so this also comes out to be very complicated. S minus 1 plus K1. Okay, this meeting will actually end in 1 minute. Then I will again restart this meeting. Into S square minus 3S plus 2. This comes over here. Okay, so this is completed. Plus 2 into K2 minus 3 into S minus 2 plus K3 minus 4 into 3S plus 2 minus 3. So Si minus A closed loop comes out to be equal to S minus 1 plus K1 into S square minus 3S plus 2 plus 2 into K2 minus 3 into S minus 2 plus K3 minus 4 into 3S minus 1. Okay, so this is what? S cube minus 3S square plus 2S minus S square plus 3S minus 2 plus K1S square minus 3K1S plus 2K1. Okay, plus S into 2K2 minus 6. So I've just multiplied this entire thing, 2K2 minus 6. And it is 2K2 minus 6 multiplied by minus 2. So that would be minus 4K2 plus 12. Okay, so this is the computation for this. So like I was kind of so this part is this part. This part is this entire part. Okay. Then I will do this K3 minus 4. So this is again what? Plus S into 3 K3 minus 12 right? And minus of K3 plus 4. Okay, so this is this part. Not seen. Sorry. This is this part. Okay, so let us add this. So this becomes equal to S cube. So minus 3 minus 1 minus 4. So this is plus K1 minus 4 into S square plus S into 2 plus 3 is 5. 5 minus 3K1 plus 2K2 minus 6 plus 3K3 minus 12. Okay. Then it is minus, so it is plus 2K1 minus 2 minus 4K2 plus 12 minus K3 plus 4. Okay. So it is equal to S cube plus K1 minus 4 into S square plus S. 5 minus 6 is minus 1 minus 12 minus 13 minus 3K1 plus 2K2 plus 3K3 plus 2K1 2K1 minus 4K2 minus K3 plus 12 minus 2 is plus 10 plus 4 plus 14. Okay, so this is the equation which we get. Okay, but what is our desired characteristic equation? Our desired characteristic equation is we want the poles be at minus 1, minus 3, minus 5. So there is S plus 1 into S plus 3 into S plus 5, right? So let us substitute it. S plus 1 into S square plus 8S plus 15. So this is what? S cube plus 8S square plus 15S plus S square plus 8S plus 15. So if you'll observe, what I'm trying to do is I'm trying to make all the S square align them. So it becomes easy when I add. Okay, so that is a way I'm trying to prevent errors. Okay, just a safety precaution. So this becomes S cube plus 9S square plus 15 plus 8 is 23S plus 15. Okay, so now we have found this complicated thing. And now we have to find these equations. We have to equate. So we get K1 minus 4 is equal to 9. Right? So what do we get? K1 is equal to 13. Similarly, we get minus 13 minus 3K1 plus 2K2 plus 3K3 is equal to 23. So 2K2 plus 3K3 is equal to 23 plus 13 plus 3K1 is again 13. So it is 2K2 plus 3K3. 23 plus 13 is 36. To do the calculator only for this. 23, 23 plus 13 plus 3 into 13. So that is equal to 75. Okay. Then we have to equate the last part, that is this, is equal to this. So we get 2K1 minus 4K2 minus K3 minus 4K2 minus K3 plus 14 is equal to 15. Right? So we get 2 into K1 is 13 minus 4K2 minus K3 is equal to 1. So 26 minus 4K2 minus K3 is equal to 1. So minus 4K2 minus K3 is equal to minus 27, or we better write it as 4K2 plus K3 is equal to 27. Right? So what I can write is I can write K3 is actually equal to 27 minus 4K2, and then I substitute it over here. I put it off over here. So what I will get 2K2 plus 3K3. 3 into K3 is 27 minus 4K2 is equal to what? 75. So this 2k2 plus 3 into 27 is, we calculate 81 minus 12k2 is equal to 75. So we get minus 10k2 is equal to 75 minus 81 minus 10k2 is equal to minus 6. So k2 is equal to 0.6. Okay. So what is left is k3. K3 is equal to 27 minus 4k2, 0.6. So this becomes equal to 27 minus 4 into 0.6. It comes out to be 24.6. So the gain vector k is equal to k1, k2, k3. It comes out to be equal to 13, 13.6, 24.6. Okay. Any doubts in this? Okay, so these are very computationally intensive, very, very stressful mathematics which has to be done because we have to write the exam. Okay, so if there are no doubts, can I proceed to the next question? Okay. Okay, so now we will consider a system. We have to represent this transfer function in canonical form and find the suitable gains to set the poles at these locations. Okay. Yeah, procedure is clear. Only implementing is very, very tedious, very, very difficult. That I'll admit. Okay. So now we have to place the poles at this location, and this is our transfer function. So they are telling us to first represent it in canonical form, and then we have to find the gains to set these poles. Okay. So let me come over here. This actually is which question? I think question 4. 1, 2, 3. So question 4. So we have told that we have to place the poles at these locations, right? So our desired transfer function is what? S. So it is minus 2 plus minus j10. So it should be S plus 2 plus or minus j10. So those are the pole locations, right? This S plus 2 plus j10 and S plus 2 minus j10 into S plus 20. Okay, into S plus 20. So if you will observe carefully, all these poles have a negative real part. Okay, that is very important based on the condition of stability. Now, if you will observe, this is a complex conjugate. So when you do multiplication, what you have to do is very simple. You have to just do the a square plus b square. Okay, the rest part gets cancelled. So this is very simple. You don't need to multiply here and there. And this is s plus 20. So this actually is what? S square plus 4s plus 4 plus 100 into s plus 20. So that is equal to s square plus 4s plus 104 into s plus 20. Okay. So this is s cube plus 4s square plus 104s plus 8 plus, sorry, 20s square plus 80s plus 104 into 20 is 2080. So when we add it, we will get it to be equal to s square plus 24s square plus 184s plus 2080. Okay, so these are the desired closed loop characteristic polynomial which we want. Okay, so now let us go to what is the transfer function we were given. We have y of s upon u of s is equal to phi upon s plus 2 into s plus 4 into s plus 10. Okay, we have it as a phi into s plus 2 into s plus 4 into s plus 10. Okay, so this is the system which we have. Now, how do we proceed with this? So we will let us expand this system. Okay, so this is what is s square plus 6s plus 8 into s plus 10. So that is equal to phi upon s cube plus 6s square plus 8s plus 10s square plus 60s plus 80. So that is equal to phi upon s cube plus 16s square plus 68s plus 80. Okay, so this is the expanded transfer function. It is no longer in the form of poles and zeros. In the form of poles, it is in the form of an expression, which is the characteristic polynomial is given here. This is the characteristic polynomial of the open loop system. Now, what is desired is we must do pole placement via state feedback, right? So we need to know what are the states. So what is done is when we want to represent it in terms of canonical form, we will take let y, okay, y of t to be equal to x1 of t, okay? And we take x2 of t is equal to x1 dot of t and x3 of t is equal to x2 dot of t, okay? So what does this mean? In Laplace, it means y of s is equal to x1 of s, okay? Then x2 of s is equal to s into x1 of s. So that is s into y of s. x3 of s is equal to s into x2 of s. That is equal to s square into y of s. Okay. So what do we do now? So why did I do all this maths, everything? Because I want to show how do you get the canonical form. You guys would have learned it, but this is just a revision. Okay, and the advantage of canonical form is it becomes easier to place the poles when the system is represented in canonical form. Okay, so what do we do is we cross multiply y of s upon u of s. We have written it as phi upon s square plus 16s square plus 68s plus 80, right? So we multiply it becomes y of s, this s cube, sorry, s cube plus 16s square plus 68s plus 80 is equal to 5 into u of s. So this is what s cube into y of s plus 16 into s square into y of s plus 68 into s into y of s plus 80 into y of s is equal to 5 into u of s. Okay. Now, how do we write this further? This actually is equal to, uh, we write it as s into s square of y of s, okay, plus 16 into, okay, this will be x3 of s, right? Okay, 16 into s square of y of s plus 68 into s into y of s plus 80 into y of s is equal to 5 into u of s. Okay, so this is s into x3 of s. Okay, plus 16 into x3 of s plus 68 into x2 of s plus 80 into x1 of s is equal to 5 into u of s. So when you take the inverse Laplace transform, take the inverse Laplace transform, what you will get? X3 dot of t plus 16x3 plus 68x2 plus 80 into x1 is equal to 5 into u. So x3 dot is equal to minus 80x1 minus 68x2 minus 16x3 plus 5 of u. Okay. So our state space representation is what? X1 dot is equal to x2, x2 dot is equal to x3, and x3 dot is equal to minus 80 into x1, minus 68 into x2, minus 16 into x3, plus 5 into u. Okay. So how do we write it as? So we write it as x1 dot, x2 dot, x3 dot is equal to 0, 1, 0 into x1, x2, x3. Then it is 0, 0, 1 into x3, minus 18 into x1, minus 68 into x2, minus 16 into x3, plus 0, 0, 5 into u. Okay, 0, 0, 5 into u. Any doubts till here? So this is the okay. So this is the representation in canonical form. Okay, there's one more thing I forgot. Okay, so this actually you should write it in a better way. Is this 5, if it was like written as 1 into 5, then it would be easier. The canonical form would be actually here it should be 1. This should ideally be 1, and your y should be equal to, y will change then. Y in that case will be equal to 5 into x1 in that case. Okay, but let it be in this format. And let us try the pole placement now. Okay, so this we have got it like this. Now, why it becomes easier is when you do b into k. Okay, your b is 0, 0, 5, right? And this is your k1, k2, k3. This is like this. This is your k1, k2, k3. So when you do now, what you want to do, you have to do a minus bk. Okay, so what is your a? Your a is 0, 1, 0, 0, 1, 0, 0, 0, 1, minus 80, minus 68, minus 16. What is your bk? It will be 0, 0, 0, 0, 0, 0, 5k1, 5k2, 5k3. Okay, so your a minus bk will be equal to 0, 1, 0, 0, 0, 1, minus 80, minus 5k1, minus 68, minus 5k2, minus 60, minus 5k3. Okay, so this is your A closed loop. So your SI minus A closed loop will be equal to S minus 1, 0, 0, S minus 1, 80 plus 5k1, 68 plus 5k2, S plus 16 plus 5k3. Okay. So now we expand it. Where is it? Oh, it's here, this space. So we write, so now we have to find the determinant. Si minus A closed loop should be equal to 0. So that would be S into S into S plus 16 plus 5K3 plus 68 plus 5K2, right? Plus 1 into minus 1 into 80 plus 5K1. So it is plus 1. So plus 1 into 80 plus 5K1. So this becomes equal to S cube plus S square into 16 plus 5K3 plus S into 68 plus 5K2 plus 80 plus 5K1. So any doubts still here? Okay, so it has become simpler. Now, what was our original equation? What was our desired characteristic equation? It was S cube plus 24S square plus 184S plus 2080. I've forgotten it already. Our desired S is S cube plus 24S square plus 184S, 24S square, 24S square plus 180S plus 2080. Okay. So when we compare, what do we get? 16 plus 5K3 is equal to 24. 68 plus 5K2 is equal to 180. 80 plus 5K1 is equal to 2080. So we get 5K3 is equal to 8. 5K2 is equal to 180 minus 68 is, I think it is 112. Is 112. And 5K1 is 2000. So we get K3 is equal to 1.6. K2 is equal to 22.4. K1 is equal to 400. Okay, so the vector K required is 400, 22.4, and 1.6. Okay. So any queries in this?
Sir, given any system,
Mm-hmm.
can we convert it into this canonical form and then can we solve? Since this doesn't involve solving equations.
Yeah, you can convert it into canonical form. It is there's a method, but that is a bit tricky. Okay. So one thing, there are two ways. Okay, there are two ways. Okay, so canonical form is useful. Okay, it is useful, right? So it would be easy if your A and B is in canonical form. It would be nice. But suppose they are not. If your A and B is not in canonical form, then you have to transform it. There will be some, you have to do some T inverse A T and T inverse B. So this will be in A canonical form. This will be a B in canonical form. So now the challenge will be you have to find your T. You have to find this T. Okay, you have to find this T. So what is the problem with finding this T is, I'll show you. Because it is very difficult, I have written it. Okay, how do I convert this A matrix and B matrix? You can see A matrix and B matrix, they are not in canonical form. I have to convert it into canonical form. So what you have to do in that case is, you have to first find the controllability matrix. This is your step 1. Okay, let me go step by step. You will understand it. sorry. So you'll find the controllability matrix. That is easy. Okay, that is also kind of easy. Then you have to find the inverse of it. Okay, your inverse of your canonical of this controllability matrix. This will be difficult if it is a third order. Second order will be easy, but third order, once you go, it takes time. It will take time. Then what you have to do, you have to select one row. Usually what do we do is we select the last row. So what is done is we select this last row. So that means your mu in that case will be this 1, 2, minus 1. Then you have to find a matrix which is mu into A, mu into A into A. So that is even more difficult. So you will get mu. So this will be your new matrix. Then you have to find the inverse of this matrix. Okay. So this is that inverse of that matrix. And then you will find this in canonical form. And this will be again in canonical form. Okay, so this is actually very painful. It is very painful to do this. You have to do all these steps, then you're converting it into canonical form. What I'd suggest is a better way would be uh, maybe a bit easier way. I'm suggesting you have your A. I'm writing. This is your A B matrix you have. Okay, what you can do is uh, mm, you have to find your transfer function. You have to find your transfer function. Suppose you will have C matrix. Okay, then you have your y of s upon u of s is equal to C into Si minus A inverse into B. Okay, so this is your transfer function. So then you have it in this form. Okay, you have it in this form, right? And if you'll observe carefully, this is s cube plus 16s square plus 68s plus 80. Okay, so these are your coefficients, right? This is your coefficients of your denominator. Your A matrix will be minus 16, minus 68, minus 80. And this is 0, 1, 0, 0, 0, 1. So directly from the transfer function, you can write this. Only thing is you have to remember this. So directly you take the transfer function and you write it in this canonical matrix. You can write it. Okay. The B actually is coming out to be 005U. That only I have to think. What was the mistake I've done here? It should actually be, what is the error? Okay. Acha. What it will be is, it will actually be 1. Okay, this will actually be 1. And the y will in this case be 5 into x1. Okay, y will be equal to 5 into x. So that will take care of the 5. Okay. And then you can easily do this bk. And the advantage with this is you have to do b into k. So that is 0, 0 into 1. Okay, let me just write it again. Because you have a, b, and c. What you find the transfer function. You find the transfer function. Okay, suppose you have y of s upon u of s. Let us take some values. This is s plus, let me take s plus b. Okay, this is s cube plus a1s square plus a2s plus a3. Okay, your canonical form, it will be 0, 1, 0, 0, 0, 1, and it will actually be in which order? Let us see, because we have done it. So it is actually minus 80. It is actually 80 minus 68, 16. So which is 80? 80 is the last. 80 is the last thing. So it will actually be minus A3, minus A2, and minus A1. This is your canonical form 1. Your B canonical will be 0, 0, 1. And your C will be equal to it will be equal to b into 1 into 0 into x. Okay, so this is your c, and your y is equal to c into x. Any doubts in this? And then what happens is the advantage is your beacon into k, it will just be equal to 0. All this will be 0, 0, 0. It will be k1, k2, k3. And your acon minus b controllable into k will be equal to 0, 1, 0, 0, 0, 1. It is minus a3 minus k1 minus a2 minus k2 and minus a1 minus k3. Okay. And when you do, and this is your closed loop. And when you do si minus a closed loop, it will be equal to s minus 1, 0, 0, s minus 1, a3 plus k1, a2 plus k2, and s plus a1 plus k3. And if you further you simplify, you find this si minus a closed loop, it will come out to be s cube plus s square into a1 plus k3 plus s into a2 plus k2 plus a3 plus k1. So it comes out to be in this format. So this becomes easier for you to solve. So this I would recommend this approach to make it easy. So I hope this approach will be considered when you're solving sums. I think this can be a easier way. It makes it simpler. So that's why it is easier when it is in companion form, right? And you can solve. So now let us go to the next question. And this is a difficult question. Okay. So it is saying consider the discrete time system. You have to find state feedback gains to achieve deadbeat control. Okay, you have to find the state feedback gains to achieve deadbeat control. So question.
Sir, what I have a doubt.
Yes, yes.
Sir, what is meant by deadbeat control?
Yeah, yeah, yeah. I'm telling. Yeah, yeah.
Oh.
So they have told we have to achieve deadbeat control. Deadbeat control means that you reach the desired output in a finite amount of steps. Okay. You reach the desired output in a finite number of steps. Okay. And this is only possible in digital control. So, you have studied about continuous time systems, right? And you have studied what is the settling time. There's a thing known as settling time. There's something known as time constant of a system. First order system has a time constant, second order system has a settling time, etc. So, what is the definition of settling time or time constant? Can you tell?
For settling time, it's defined as the time at which the y of the output settles to the desired value within the range like plus or minus 2% error.
Okay. 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 And your time constant? So like your time constant is how much time your output takes to reach 63.3% of your desired output. Okay. But if you will understand is that in continuous systems, reaches, okay, theoretically, output reaches the desired value only at t tends to infinity. See, it has reached plus or minus 2%, and we say, okay, it has reached. But only as t tends to infinity, then only we say that your output has actually reached your steady state. Right? Any doubts in this?
No, sir.
Okay, so this is one thing which happens in continuous time systems. But in discrete time systems, in digital systems, there's a condition. And if we satisfy that condition, we can say that my output will reach where we want it to reach within this finite number of steps. Okay, so that is known as the deadbeat control. And for deadbeat control, what we need is, okay, let us say for a discrete time system, discrete or digital system, what is the condition for stability? Can you tell me? Like what do we mean by we like for continuous time system, the condition for stability is like the poles or the eigenvalues should have a negative real part, that is they should be in the left half of the S plane. What is the case for discrete or digital system? What is the condition for stability? Okay, so anyway, I'll tell. So for discrete time system, we consider the Z plane. Okay, and the poles need to lie within the unit circle. The pole should lie within the unit circle. Okay, that is the criteria. And if you want to do deadbeat control, what you want to do is you want to place all the poles at the origin. You must place all the poles at the origin. And if you can do that, then within a finite number of time, and that is usually dependent on the order of the system, the output will settle at the desired value. So that is the guarantee of deadbeat control. Hmm. So I hope this condition is clear. The deadbeat control means you place all the poles at the origin. This is for digital system only, it is valid. All right. So let us go to the question. We have xk plus 1 is given by this expression. And we have to find the gains so that we can achieve deadbeat control. Right? So this would be which question? Question number 5. 5. Xk plus 1. What is this? A 1 2 4 1 2 4 2 1 0 3 1 2 3 1 2 xk plus 0 0 1 u of k. Okay, in discrete time system, we represent in terms of k. K is the kth sample, etc. In terms of k, right? So we have to find the So again, we have A minus BK. This will be our representation. And that is what 1, 2, 4, 2, 1, 0, 3, 1, 2. And since this B is similar to what will be in a canonical form, we can write it as 0, 0, 0, 0, 0, 0, K1, K2, K3. Okay. So what do we get? We get A minus BK is and which is my A closed loop is equal to 1, 2, 4, 2, 1, 0, 3 minus K1, 1 minus K2, 2 minus K3. Now we have to find the characteristic polynomial. Okay. So we have to do Zi minus A closed loop. This time we have to use the term Z. We cannot use the term S. Okay, because we are doing digital. Right? So Zi minus A closed loop will be what? It will be equal to Z minus 1 minus 2 minus 4 minus 2 Z minus 1 0 Z plus K1 minus 3 Z plus K2 minus 1 Z plus K3 minus 2. Okay. Then we equate, what do we get the determinant of Z minus A closed loop? That will be equal to Z minus 1 into Z minus 1 into Z plus K3 minus 2 plus 2 into minus 2 into Z plus K3 minus 2 minus 4 into minus 2 into Z plus K2 minus 1 minus Z minus 1 into Z plus K1 minus 3. So this is very complicated. Okay, so how do we solve this? So if you see, this can be written, this Z plus K3 minus 2 is common here. This and this is common. So we write Z plus K3 minus 2 into Z minus 1 square minus 4. Okay. This we have simplified. Then plus 4 into minus 4 to minus 2 is 8. 8 into Z plus K2 minus 1. Then minus Z minus 1 into Z plus K1 minus 3 is what? Minus of Z square plus K1Z minus 3Z minus Z minus K1 plus 3. Okay, so this is what we get. Okay, so now let us expand this further. We get Zi minus A closed loop is equal to Z plus K3 minus 2 into Z square minus 2Z plus 1 minus 4 plus 8Z plus 8K2 minus 8 minus of Z square plus Z into K1 minus 4 plus 3 minus K1. Okay. So now when we expand this, this becomes 3Z cube minus 2Z square minus 3Z plus K3 into Z square minus 3, sorry, minus 2Z into K3 is minus 2 K3 into Z, and minus 3 into K3 is minus 3 K3. Then minus 2 into Z square should be, this would be minus 2Z square plus 4Z. So minus 3 into minus 2 is plus 6. Okay. Plus 8Z plus 8K2 minus 8. 8 k2 minus 8, then minus z square, then plus z into minus k1 plus 4 plus k1 minus 3. Okay. So this when we add becomes z cube plus z square into k3 minus 5 plus z into 4 plus 8, 12 plus 4, 16 plus 3, 16 minus 3 is 13 minus k1 minus 2k3. Then plus 6 minus 8 minus 3 is minus 2 minus 3 is minus 5 minus 5 minus 3k3 plus 8k2 plus k1. Okay, so we got this, and this is our A design. Okay, A design of Z, we got it in this format: Z cube plus Z square into minus 5 plus k3 plus Z minus k1 minus 2k3 plus 13 plus minus 5 plus k1 plus 8k2 minus 3k3. But our design Z actually should be Z cube, right? So when we equating, we get, so this is because we want deadbeat control. Okay, and what do we get? Minus 5 plus k3 should be equal to 0. So this implies k3 is equal to 5. Then we want minus k1 minus 2k3 plus 13 is equal to 0. So we get k1 is equal to 13 minus 2k3. So it is 13 minus 2 into 5. So it is 3. Then we get minus 5 plus k1 plus 8k2 minus 3k3 is equal to 0. So we get minus 5 plus 3 plus 8k2 minus 3 into 5 is equal to 0. So we get 8k2 minus 2 minus 15 is equal to 0. We get 8k2 is equal to 17. So k2 is equal to 17 by 8. Okay. So this is how you have to solve such sums. There's no alternative I have found till now. Any doubts? Okay, so we'll proceed to the next question. That will be question 6. We'll go to question 6, right? This is our system A, B, and C, and we have a gain vector K, which should be K1 into 0. No, it should be K1 into 1. And so we have A, which is equal to there's some issue with that thing. A is 2106. So A is 2106, right? And B should be equal to 10, 10, and C should be equal to 2, 3. And the gain K vector is what? K1 into 1. Okay, this should be K1 into 1. So now how do we solve it? They are saying, is there any condition when my system becomes non-observed? Okay. So how do we, like, what should we do? Is the original system controllable and observable? That we can find. Okay, how will we find that? AB, if we do, AB is what? 2106 into 10. So that will be 2, and then 0 into 6, so it is 0. Right? 2 into 1 is 2, 0 into 1, and this is there. So Q, this B comma AB is equal to 1020. So is this system controllable? If we made a mistake. Okay, this system is not controllable, so we cannot consider the state gains. Well, let me modify the question a bit. Let me make it B is 0, 1, and then let us proceed. So this will be 0, 1, then it will be controllable. So this will be 2 into 0, so this will be 1, 0, and this 6. Q will be B, A, B, that is 0, 1, 1, 6. Okay, and this determinant of Q is not equal to 0. So now the system is controllable. Okay, so sorry, I did not consider, I think I made a mistake while making a question. Okay, so this is Q, our controllable matrix. And now we have to find what is a closed loop thing. Closed loop is given by A minus BK, right? So that would be A is given by 2106 minus B is 0, 1 into K1 into K2. So this becomes equal to 2106 minus of 0, 0 K1 into K2. This is a closed loop. So A closed loop will be given by 2, 1 minus K1, 6 minus K2. Okay, so these are, we are told to take K1 and 1. So we are told that K2 is equal to 1. So A closed loop will then be equal to 2 minus K1, 1, and 5. So these are A closed loop, right? So Si minus A closed loop will be given by S00S minus 2, 1 minus K1, 5. So that is equal to S minus 2 minus 1 K1 S minus 5. So Si minus A closed loop inverse will be equal to S minus 5 S minus 2 1 minus K1 upon S square minus 7S plus 10 plus K1. Okay. So this is our matrix Si minus A closed loop. And our C matrix is given by 2, 3. Okay. So our system transfer function will be what? C into Si minus A closed loop inverse into B. So what is our C given to be? 2, 3. C is 2, 3. And this is S minus 5, 1, minus k1 into s minus 2 upon this transfer function mod of si minus a closed loop into b. B is given by 0, 1, right? So what I'll do is I'll multiply with b first because that is simpler. So my transfer function is what? 2, 3, s minus 5, 1 minus k1, s minus, sorry, I didn't multiply on it. So it is what? S minus 5 into 0 is 0, and here 1. Minus k1 into 0 is 0, and here it will be s minus 2. Okay? Upon si minus a closed loop. So that will be 2 plus 3 into s minus 2 into si minus a closed loop. So that comes out to be 2 plus 3s minus 4 upon si minus a closed loop. The determinant. So that is equal to 3s minus 2 upon this is what? S square minus 7s plus 10, s square minus 7s plus 10 plus k1. Okay. So this actually is given by 3 into s minus 2 by 3 into s square minus 7s plus 10 plus k1. Okay, so this is the equation. Now what I want to put across is at a certain k1, assume this actually is 3 into s minus 2 by 3 into s plus p1 into s plus p2. Assume at a certain k1, what happens? Either p1 or p2 is equal to minus 2 by 3. Okay, it is equal to minus 2 by 3. Then what happens? Y of s upon u of s will be equal to what? 3 upon, let's say, s plus p I. It could be p1 or p2. So then what has happened? There's something known as pole zero cancellation has occurred. And if that has happened, if pole zero cancellation has occurred, then the system is no longer observable. Okay. So these are advanced concepts. So if you have any doubts, you can ask me. I can again repeat it. It will become easier. Okay, so let us check. This is our discrete-time system. Okay, so I'll do a brief recap of what I have done in this session. So I have considered a linear time invariant system. X dot is equal to ax plus bu. We found that it is unstable. That this system is unstable since the eigenvalues, one eigenvalues is in the right half of the S-plane. And because it is in the right half of the S-plane, that system is unstable. Now, if I use state feedback, can I control it? I could do the design, but a simple thing to do first, precautionary thing which we must do is first we must find a controllability matrix. Okay, we find a controllability matrix. And how do we find a controllability matrix? We do B and AB. Okay, because it is second order. And when we found out the controllability matrix, we found out that the determinant of Q is equal to 0. That means its rank is not 2, its rank is 1. So it is no longer a full rank, and hence the system is uncontrollable. Since the system is uncontrollable, it is pointless to design state feedback for it because we cannot control all the states of the system. Okay, there's another case in which some states are controllable and some states are stabilizable. So if the uncontrollable states are stabilizable, then we can control the states which can be controlled, and we will assume that, and what will happen is the states which cannot be controlled, they will decay to 0. Okay, so we will not get the best performance, but we can get some acceptable performance, but we can make sure that the entire system can be stabilized. Okay, so that is a condition for stabilizability. Now, we'll consider another LTI system, which is given by this equation. X dot is equal to minus 1053x plus BU. Okay, we have the settling time and we have the damping. So what do we have is the transient specifications. So once we have the transient specifications, what do we find? We find our zeta is given to us, we find the omega n. After we find that, we find the characteristic polynomial is found, okay, which is given by s square plus 2 zeta omega n s plus omega n square. Once we find this characteristic polynomial, we will, so we have found this polynomial. Then we use the state feedback law, u equal to plus kx. So I can use u equal to minus kx also, I can use u equal to plus kx, but I must remember what have I considered. This one I've used plus kx, so my closed loop A matrix will be equal to A plus bk. So this A plus bk, so this is my A closed loop. Okay, this is A plus bk. So we have B, we have K. From bk we get these equations. And this is my x dot is equal to A closed loop into x. Now what I must do is, I have to find the determinant of Si minus A closed loop. So I compute that matrix, I equate it to 0, and then I will continue, I will expand this. Okay, I will expand this. And then I will get it in terms of S square plus S and the constant term. Once I get that, I equate it with the original desired characteristic polynomial, with my design equation. And what I will get in that case, I will get the values of K1 and I will get the value of K2. Okay, so both these values will be found through this method. Okay. So we tried actually another method using place and we weren't able to get. Let me check. This is the A matrix. These are the specifications. When we put place, it comes out to be 0.7826, 0.8261. When I did Bhaskara algorithm, I got 50 by 69. So, A, what is 50 by 69? 50 by 69 is 0.7241. And 57 by 69 is 0.8260. Okay, what was the mistake? Okay. So, if you will observe, I have used the same equation. So these are my system matrices. Okay. These are my transient specifications. Okay, so from that I find what is the natural frequency. And then I find out what is the damp frequency. After finding this is my pole 1 and this is my pole 2. Both of these are my poles, pole 1 and pole 2. Then what do? I define a vector of pole locations. Okay, and then there's this MATLAB command which provides me the gains. Okay, this is my gain k. This actually is my gain k. So if I'll run it, this is my gain k. It is 0.7826 and 0.8261, right? So what has happened is close by 0.2741, 0.8268. There may be some slight here and there, some mathematical approximation, rounding off, etc., but it is very close, right? So this we found using Ackermann formula. So this has been found using Ackermann's formula. There's something known as Busguru algorithm also, but that's a different way. So this, there is some error which is needs, probably I made a mistake in solving the sum. Okay, there might be some numerical error which happens. Okay, so what does Ackermann's formula do is we find Q inverse, controllability matrix we find, and its inverse and D of A. So this is a desired polynomial. So we get A square plus 2A plus 4I. We add it. Once we get that, then we have B comma AB. And this is a controllability matrix we are finding. Q inverse we have found. Q inverse DA we do. And we do 0, 1 of that. Okay, and we get these equations. Okay, so this is one way. And we have also verified with MATLAB. Next thing is we can do pole placement. Question 3. This is my system matrix, and these are third order system. And this is the B matrix. We find this BK, A minus BK, and what I've come to the conclusion is if the B matrix was made in canonical form, A matrix was already given in canonical form, then these questions would have been easy, much more easier, much more intuitive and understandable. So this I will keep for my later next year probably. So now we find again A minus BK is found, and then we find a closed loop characteristic equation by doing Si minus A closed loop is equal to 0. Once we get that, then we equate it with a desired characteristic equation. And from that, we get the values of this k vector. K1, K2, K3, we get it. Okay. So next, I considered this sum where we first represent this transfer function in canonical form, and then we find suitable gains. Okay. So this is a desired characteristic polynomial, and then this is the transfer function of our system. We expand it. It was in the poles. We made it into the form of a polynomial, which is given over here, and then to convert into this companion form. Okay, there's this method. This method was used. We find the inverse Laplace transform, etc., and we get the matrix in terms of canonical form. Sorry, this is not canonical form. This is in companion form. Okay, BK is found, and then we find the closed loop transfer function. We now don't need to do any mathematical algebraic equation solving, or we don't need to solve again a set of simultaneous equations. We can just equate it and we're finding this. Okay, so this is not canonical form, this is companion form. Okay. I also told about how the steps to find it in companion form, and that is really difficult. Okay, so best would be you have the ABC matrix, you find the transfer function. Once you find the transfer function, then you convert into canonical form into companion form, okay? And then you can solve it, and then you can make it easy. So you get it in terms of this. So this is becomes very easy for you. So you have actual control to place one pole here, another pole there, where you want. It is very easy for you now to decide, right? Then the next question was about deadbeat control. So deadbeat control is only possible in digital control systems, and this occurs when all the poles are placed at the origin. Okay, so this is not always possible. It is very, very unlikely, and there are certain problems which occur is if you want to do deadbeat control means your control effort will be very high. It will be very large. And when your control effort is very large, what will probably happen is your actuator may get saturated. And when your actuator saturation occurs, then your system is like gone out of your control. It is no longer being actively controlled. Okay. It is just behaving. It is behaving as per some saturated value, but it's not being actively controlled by your controller in that case. Okay, so that's why it is not always recommended and it should be carefully done. But this is just a theoretical perspective that you can use deadbeat control to, you can achieve finite settling time. And this is only possible in terms of digital control. In continuous time control, only when t tends to infinity, you can reach your steady state value. Okay, theoretically. So this is the xk plus 1 is equal to a into x of k plus b into uk for your digital system. We again do the same thing. We find again the closed loop poles, etc. And we equate it with the desired polynomial. And we get the values of k1, k2, k3. Similarly, next we considered again a second order LTI system. And we found a controllability matrix. We found it is, there was some mistake in A, B, and values. I changed it because I had not properly considered it. Then I rechanged the system. And then we found it is controllable. And then these are the closed loop A matrix. These are the closed loop transfer function, polynomial. And then the overall system is found. And then I explained that when we have pole zero cancellation, what happens is one of the modes disappears. It is kind of cancelled. So the effect of that mode is not visible to us anymore because it has got cancelled. So when this happens, the system is no longer completely observable. We can observe one mode, but we cannot observe the other mode. Okay, so this also has to be avoided. It is preferable to avoid such a situation. So that we must also consider when we are determining our state feedback. Okay. So also sir has taught about Busbaro algorithm also, how there is some certain way which you can find the things. And sir also explained for pole place for multi-input system. Okay, multi-input system will give a non-unique solution. If you have a single input, single output system, you will get a unique solution of K. If you say that my desired pole should be at this location, you will get a unique solution for what gains you require. But if you do for a multi-input system, then your gains, there can be a multiple range of gains are possible. Okay, so that also sir has shown through an example. Then the various ways. How do I select what should be my pole location? Now I am say it is given that you must place the poles here, you must place the poles here, etc. But how do I know like what criteria I must use when I'm doing my project and I want to control my system and where should I set a closed loop pole location? So then there are major criteria. One is you do a dominant second order design. So second order design is very, very useful and it is very, very well standard way approach. We consider two poles which are a dominant pair of poles. So they are close to the origin. So they actually dominate the transient response. And the other poles are comparatively far. So comparatively far is what they do in the design criteria is like the pole should be at least 10 times further away from the dominant pair of poles. Okay, that is one criteria. Another criteria is ITA design where we are trying to minimize the energy. It's minimizing a cost function. Okay, and how these are the polynomials. Second is Bessel filter, which avoids overshoot completely. Okay, and another criteria is you can use Butterworth filter. Okay, poles are placed located at uniform angular position with respect to the negative real axis. But if you go for higher number of poles, then this can be a bit tricky. there is a poles could lie very, very close to the origin. And when the poles lie very, very close to the origin, like it's at close to the imaginary axis of the S-plane, we see that it is at the verge of instability. So we have to be very, very careful when we select our close to pole location. Okay, so I hope this session was very informative. I will upload this video and these notes also on the drive. Okay, so thank you for joining. All the best.